right. How's everyone doing? I'm sorry. It's like almost 71 in here. I usually keep it at 69.
There's fine in here.
It is cold outside. It was 17 degrees Fahrenheit when I woke up, and then it was 13 degrees Fahrenheit when I came to school. We're supposed to have a low of 10 today, and I don't know what the high is, like 27.
It's all about the wind chill.
Okay, well, that actually is going to play into what we're doing today. We're talking about, hey, nice. Not sure why I have that. We're talking about thermodynamics here. And so we're going to talk about temperature and what it means. So we've already identified that temperature is a measurement that tells us, if it's like the air temperature, it's telling us about the average kinetic energy of the molecules, how fast they're moving. And so if you think about it, if the temperature is telling us about how fast the molecules are moving, how much kinetic energy they have, 1/2 mv squared, so how much speed, what's the minimum speed that a molecule could have? If temperature is telling us about the average speed of the molecules, what's the minimum speed that a molecule can have? Not moving. It can have a minimum of 0 kinetic energy not moving. And so that means there must be a minimum temperature, the lowest temperature when...
Wouldn't that be absolute zero?
That's the definition. Well, it would be the definition of absolute zero if it wasn't for quantum mechanics. Quantum mechanics says that they can't actually come to a full and complete stop in some situations. So absolute zero is when you reach the lowest possible energy state, which for this class we will simply say all motion ceases to exist, even though on a quantum level it's not true. So that means temperature has a minimum. Now what about a maximum? What's the maximum kinetic energy a particle can have? Is there? Great answer. No, there's not. There is no maximum. There is a maximum speed, the speed of light, but it turns out that when you get up to that kind of speed, the kinetic energy equation is slightly different. And as it gets closer and closer to the speed of light, the kinetic energy just keeps going up. So you'd be infinite infinite kinetic energy if you reach the speed of light for a particle. So the upper limit on energy is there is no limit, hence temperature has no upper limit. It can just keep going up. So we have a scale that starts at some minimum value and goes up forever. And so that's why we have this idea of absolute zero. Absolute zero is the absolute minimum temperature something can reach. So here in this classroom, we are saying it's roughly 71 degrees Fahrenheit. We could cool it down. We could get down to, if we walked outside, it's probably around 15 degrees Fahrenheit right now. That's much colder. You all have a good feel for that, right? What's the coldest anyone's been in?
Like us personally?
Yes. Like we walked outside when it was this temperature.
-8. Like that was the
That would be like this past week.
I mean, like,
Is this past week the coldest you've ever had?
Yeah.
Probably for you too, huh? No?
Well, I guess if we count like a couple years ago, it was the -25 wind chill. But I don't know if it's like, because that's just the wind chill. That's not the actual temperature.
Right. Okay, so let's, my first year in graduate school, it was like -30 something. And then with wind chill, it was like -50. So that's Washington State for you. It's
-21 with a wind chill with -50.
That's brutal.
I don't think I went outside though.
Yeah, they say like, you could get frostbite it was up in Bemidji last week, or we could go tomorrow or today. It got down to -60 with wind chill. They said if you go out there for like 30 seconds in that, you could have frostbite, something like that. I had a colleague who went to interview at what was that Canadian University College. It now has a different name that I can't remember. Berman or something like that. And they said, this year we only had 4 days where it was too cold to walk outside. He was like, I think I'll stay at my college in California. So we know that when it gets really cold, it's dangerous. But it can get much, much colder than this. Absolute zero in the Fahrenheit scale is around minus 460 Fahrenheit. It's way down there. So we're going to learn a little about that today. So first, just our basic understanding of temperature. You know, put your hand in something cold, you feel cold. That's how we define it. Hands in something hot, you feel hot. But then we've been able to relate that to motion. Now, if I put it in water, cold water is not moving as fast. Again, it's not the same relationship with kinetic energy, but still proportional kinetic energy. So cold water has the molecules moving more slowly. Hot water has them moving more rapidly. You put your hand in that hot water, it transfers energy by those molecules hitting you. And as you know, it can cause damage if they're transferring too much energy, or if they're going slow, your body is going to be giving them energy when they hit, and it takes energy out of your hand. That can also cause damage. In fact, when I was in graduate school, to make cash on the side, I participated just about every psychology research thing that they advertised in the Daily Evergreen. And one of them was measuring our perception of pain compared to people who were hypnotized. I was in the group that was unhypnotizable, because you have to really want to be hypnotized. Anyway, do you know how they create pain for psychology experiments? Ice. They put my hand in a bucket of ice water for 60 seconds. And then they say, how bad does that hurt on a scale from 1 to 10? That's how they induce pain, because you're losing all of that energy, and your body responds to that energy loss. So how do molecules have energy? If it's what we call a monatomic, these are terms that in chemistry are going to become important to us. Monatomic molecules are molecules that have just one atom. Remember, I talked about molecules, I think, on Friday. So monatomic molecules tend to be things like the right column of that periodic table in the back of the classroom. Helium, neon, argon, krypton, xenon, radon. Those are all monatomic. They're just a single atom hangs out by itself and it's happy as pie. Other things tend to form bonds. You can have hydrogen atoms by themselves, but hydrogen molecules are two hydrogen atoms bonded together. So if it's monatomic gas, then all you can have is kinetic energy. But if it's diatomic, like hydrogen or nitrogen or oxygen, those are all two atoms that are bonded together. In that case, you could also have rotation, and you can have vibration. And so that's why the equations aren't always just simple for translating from temperature into the speed, because depending on the type of molecule, you can have energy in different ways. We call them degrees of freedom. But still, temperature is proportional to the energy. And yeah, notice for a solid, the temperature is telling you how fast the particles are vibrating and jiggling as they stay in a fixed position. Solids, the atoms aren't moving around. In liquids, the atoms are moving around, and it's how fast the particles slide past each other is what the temperature is telling us. And of course, gas, we've already talked about extensively. So how do we measure thermometer? Me, thought, first put. Let's do things that are stupid first, just to rule them out. Okay, too much gas, we'll start. So one way I can measure temperature is just put my hand in there, right? Ooh, hot. And not very accurate, except for telling me hot versus cold. And so we have other things. How would you measure the temperature of this? Okay, Hosanna said with the thermometer. What did you say, Bryson?
I would feel it.
Bryson would feel it. You know, I feel like I have quite the distinction in that when I was working in the lab, I gave myself a burn by touching a hot thing and a burn by spilling the nitrogen on me in the same day. It's kind of, a good day for me. Okay, I could touch it like Bryson said, but I would be more likely to do what Hosanna said and put a thermometer in there. Okay, so just go like this. Yeah, it's gonna tell me, ooh, that's hot. By the way, here, I'm what, 4 inches away? Not a problem, it's warm. What happens if I put my hand 4 inches above it on top? That would be bad, right? Why is that?
Because the gas is going upwards and so pushing all the heat. It's more
But heat already naturally rises.
Okay, we say that heat rises, but what Hosanna said is the technically correct thing here. Hot gas expands because the molecules are moving faster, they're bouncing off of each other harder. And because the hot gas expands, what happens to its density? It actually is going to increase because density is the mass per volume. If it expands, the volume increases. And so, wait, which one did you say? It's decreases the right answer. It's decreases the right answer. The volume increases. I said, see, it actually increases the volume increases. I said density though, not volume. So yes, the volume increases, which makes the density go down because you have the same mass but bigger volume. And so the hot air is less dense than the air around it. And what do we learn about density and floating? Less dense things float on more dense things. So the hot air floats on the cold air because it's less dense. This is actually a major principle in weather. The hot air expands and it floats up. So if I put my hand over the top because the hot air is going up, it's going to be much worse. Well, here's another way that we can measure temperature. Now, we often take something like a thermometer that has alcohol in it. And that alcohol will expand when it's heated up. So here's an example of expansion when things heat up. Same idea as the alcohol thermometer, except for I'm using metals. So the ball fits through the hole. Now I'm going to heat the ball up. I totally should have a glass filled with water because it's fun to put it in water after I'm all done. What should be happening to this ball as it heats up? Okay, it's not going to get hot enough to turn red, but that would happen, yes. It should expand. Just like the air, when you heat it up, the molecules are moving faster. Even though they're jiggling in place, they're bouncing off each other harder. Imagine you have a bunch of people in an elevator. If everybody's just standing still, you can be pretty close. But if people are going crazy, you can't fit as many people in there because they're bouncing off each other and creating more space between them. Okay, this should be hot now. I've talked long enough. Now it won't fit through. How can I make it fit through?
Heat that up.
Okay, there were two answers, both correct. I could cool this back down or I could heat the ring up. So I'm going to heat them both up. I remember it takes a while, so it's not like I can instantly put it through. But if I heat up the ring, the hole in the ring will expand just the same as the metal does. So let's get closer.
But, so does the ball only expand to a certain diameter?
Hey, they're ready to go through now.
And I was going to say, since you're all up.
It actually is getting to the point where part of this is starting to glow a little red. Okay, so now it fits through quite easily. Because both of them are hot, both of them have expanded, and you see a little bit of red. Obviously, I can't put those in the tabletop or trouble ensues. Yes?
So why is it then that when you heat, or not heat, when you take water and then you freeze it, so that it expands?
That is an interesting question, one that we will answer in the chemistry section of the class. Because it's kind of complicated.
Yeah.
But water is different than everything else. Well, almost.
Everything else acts like this, it's just
Yeah.
water.
And water only acts like that from 4 degrees Celsius down to I don't know what temperature, and then it becomes normal again. Question?
Wouldn't it just be this, ice crystals, so they take up more space?
It actually has to do with the the hydrogen bonds and the way they make the molecules actually go into a stacking order that is not as tight as it would be if they didn't have hydrogen bonds. That's the fundamental reason. But we obviously have to have some chemistry down before that can make sense. Garden thermometers. You guys know the garden thermometer. You look out there and it's got the little needle that goes like this. And if you look in the back, you see this big spring. Yes? No? Sure, maybe. If you've ever seen those, hopefully you wondered how they work. Me as a kid, this didn't involve cats or any other animals. I wondered how in the dickens that thing worked. It looked like just a spring. Well, here's an example of how that works. So here I have a piece of metal. I have no front row students today. Well, no, I have one. So if you look at the metal, well, front row student. See this side here and this side here. Do they look alike? Okay. This side is more shiny. This side is more coppery, right? Okay, this well. This one here is a grayish color. This one here is an orangish color. So there's something different about the metal on each side. That's actually an important part of this, which is why I had you look at it before instead of waiting until it's red hot. Because this will turn red hot. Now I'm going to put this in the flame. And what happened? Why is it curling? Now it's cooling off and it's uncurling. What is happening here? Okay. What should happen to the molecules when I heat it up? They're moving faster, so they push on each other and expand. But there are two different kinds of metal. And the different kinds of metal expand at different rates as you heat them. And so this side here that's orangish in color, it expanded more. This side here that's gray in color didn't expand as much. They both expanded, but the orange more. And so if you have two things that are together and make one side longer, they're going to curl because you have a bigger circumference on the outside than on the inside. And so this curls based on how much each expanded. That's what's going on with the garden thermometer. You have a really, really long piece of this wound up like a spring, and it's going to tighten up or loosen up. The hotter it gets, the tighter it's going to be wound. The cooler it gets, the more it's going to unwind.
So if we heat it up to, is there going to be a certain temperature that it heats up to before straighten it?
Well, I straighten it at room temperature, so if I heat up more and more, it just goes tighter, tighter.
Oh.
And so I get down this temperature. Of course, if I put it in ice water, it should curl the other direction a little bit. So that's another way of measuring temperature. Okay, that's it for the fun today.
That thing's loud.
What was that?
That thing's loud.
Yeah, it is. It is. Okay, so we have one kind of thermometer that has to do with the expansion of metals. We have others that have to do with expansion of liquids, the mercury thermometer or alcohol thermometer. And you can also make ones that have to do with expansion of gases. But there's other kinds too. Have you ever been to the doctor's office and they like take this thing and put it in your ear and they measure your temperature? I believe those are actually using infrared radiation. They are looking at light coming from your body. Because things that have a temperature that's really hot, as you saw, as Hosanna talked about, this thing glowed red. When things are hotter, the emission comes into the visible range. Our bodies aren't absolutely zero. We have a temperature, and because of that, we're actually giving off radiation, but it's not in the visible light. It's in infrared, so they can actually determine temperature by looking at infrared radiation.
So we're glowing.
We are glowing. Funny, okay, I think it's a funny story. You guys have probably watched on like the news when they have some kind of armed conflict, they show you these night vision pictures of what's going on. You ever wondered how they make those? No? Just magic?
Well, if it's green or if it's infrared, it's
It's actually not different. It's using the same technology. It's just one is more advanced version of the other. In both cases, they're looking at the infrared radiation, the radiation given off of things because of their temperature. So if it's green, they're just looking at, this is hot, this is not. If you have different colors, the different colors are telling you how hot they are. So the different colors is a more advanced version of the same thing. But they're looking at the radiation given off by things that are hot by looking in the infrared spectrum. So Sony came out with a camera they called the zero lux camera. Lux is light flux. It's measuring how much light comes through. So it was saying a zero light camera. It would allow you to take pictures in the dark. They have these cute commercials where somebody's going to make a sandwich in the middle of the night. Instead of turning the lights, they're using their little camcorder to see their way through the house. And they look at the sofa, and there's a dog and a cat cuddled up together, The voiceover says something like, you never know what's going on in the dark. Well, now you can with the Sony Zero Lux camera. There's a problem with that, though. There are perverts in this world. And they realize that our bodies give off radiation based on our temperature. Different parts of the body give off different temperatures and whatnot. And it's mostly our bodies, not our clothes, that are giving off the radiation. And so people would take these cameras and put on filters to block the visible light so they can't see anybody, but they can see the infrared, they can see the radiation coming from their bodies. And so then they could get videos of people's bodies when they're walking around wearing clothes, which is really pervy, right? And so they had to break their technology because they didn't think that people would do stupid things like that. But that's because giving off light is something things do when they're hot. Thus, it's a way we can measure temperature. So temperature scales. The temperature scale that was first developed, that we talk about at least, is the one developed by Gabriel Fahrenheit. Fahrenheit used, it depends on who you talk to, what history source you read, what he used. It could have been the temperature of seawater and ice mixture near his home. That's the general story I've been told. I've heard different stories, right? So these are not true. Used as a reference point for 0 degrees, and used, one story I heard was the basal body temperature of a bovine. Another one was the basal body temperature of his wife. But he used one of these two things to measure 100 degrees. So he had a scale that had 2 reference points, 0 degrees and 100 degrees. And he measured the difference and made a scale to calibrate that. And so that's the Fahrenheit scale. And then notice the time there. He was born in 1686. Anders Celsius was born in 1701. So 15 years later, Anders Celsius was born after Fahrenheit. And Celsius made his own temperature scale. And this part's a little tricky. How many people are somewhat familiar with the Celsius scale? Like, numbers mean something to you in Celsius? Okay, good. That's more than half the class. Well, here's the thing that's really crazy. Despite what it says up there, Anders Celsius set the temperature of boiling water to 0 degrees and the temperature of freezing water to 100 degrees. Okay, Hosanna rightly said,
That's confusing.
That's confusing. Right? That's not right. Because then the higher the number, the colder it gets. And so absolute 0 is going to be some number up here, and then there's going to be no minimum. And you're going down in numbers as it gets hotter. It makes no sense. So notice that Celsius died in 1744. Within a year, that scale was turned over after he died. And so the Celsius scale that we know today, and I say that we know today, the Celsius scale that was in existence when I was born had 0 degrees Celsius defined as the temperature of ice water mixture. You have pure water, and you have some that's frozen and some that's not, at 1 atmosphere pressure. The air pressure makes a difference here. That was the definition of 0 degrees Celsius. And 100 degrees Celsius, the definition was if you're boiling that same water, the temperature it is when it boils. Now that's a nice calibration because you have 2 things that are very reproducible. But I said that was the definition when I was a boy. When you were girls and boys, or girls and boy, the definition was different because when I was in grade school, they changed actually grade school, when I was a young child, they changed the definition so now, instead of 0 being the reference point for Celsius scale, it's what we call the triple point of water. 0.01 degrees Celsius is the temperature no matter where you are in the world. If you lower the pressure, you will reach a point where you have ice and water and steam all existing together. That's called the triple point, and it can only occur at one pressure and at one temperature. So that's perfectly reproducible. And so that's actually, it's when I was a kid, we called Celsius also centigrade, and it confused me. What was the difference in Celsius and centigrade? There wasn't a difference, but I didn't know that. The Celsius scale is technically no longer a centigrade scale because its calibration is based on 99.99 degrees instead of 100 degrees. Just a trivial point. Please don't put that on your potential test question. It's too trivial to put there. So the Celsius scale is a more reproducible reference set than the Fahrenheit scale. Because of that, the Fahrenheit scale is now defined based on the Celsius scale. So notice here it says for the Fahrenheit scale, 32 degrees Fahrenheit is the freezing point of water, 212 degrees Fahrenheit is the boiling point of water. So if you look at my thermometer here, you have 32 degrees Fahrenheit is the same as 0 degrees Celsius. And likewise, boiling water is 100 degrees Celsius or 212 degrees Fahrenheit. Now, I think somebody was already complaining about having to convert between one and the other. The conversion isn't actually hard. The difference between these 2 points is 100. Here's something that's totally not important to you. The C with the degree sign after means a change in temperature. Degree sign first means the actual temperature. Oddly enough, this picture has it reversed. This side here, between 212 and 32 is 180 Fahrenheit degrees. So a temperature change of 100 Celsius degrees is equal to a temperature change of 180 Fahrenheit degrees, which gives us an easy conversion factor because 180 divided by 100, of course, that would be 18 divided by 10. Divide both sides, both top and bottom by 2, and that's 9 over 5. So that gives you a factor of 9/5 when converting into Fahrenheit. So if I take the temperature Celsius and multiply it by 9/5, I'm halfway there. The only thing I have to do after that is 0 degrees Celsius is 32 Fahrenheit. So if temperature Celsius was 0, I'd have 0 for this. I have to add 32. And that gives me the Fahrenheit temperature. So the Fahrenheit temperature is 9/5 the Celsius temperature plus 32. Now, one thing to note here, a change in 1 Celsius degree is roughly equal to a change in 2 Fahrenheit degrees. So if you're reading temperature on the Fahrenheit scale, you have, a change in 1 degree is a smaller change in Fahrenheit than it is in Celsius. So in Celsius, they're much more likely to talk about decimal point. It's 20.5, whereas in Celsius, we're more likely to just say it's 71. Because the Celsius degree is a bigger difference between going up 1 Celsius degree. So that's how we convert from Celsius to Fahrenheit. If you want to go the other direction, forgot which program I was in. If you want to go the other direction, you simply have to subtract 32 from both sides and then multiply by 5 and divide by 9. So temperature Celsius is equal to that. Those are the same equation, just solved for a different variable. So shifting back and forth between the two is not a difficult task. What makes life more fun? Well, we talked about absolute zero. There is an absolute zero temperature, and when we're doing our work, oftentimes we need to talk about the temperature in an absolute scale. In a scale where 0 is the minimum, and then it goes up. So for that, we have Lord Kelvin's scale that simply takes absolute zero. Absolute zero in Celsius is minus 273.15. I don't have the 0.15 here. So I'm just going to put minus 273.15 degrees Celsius. Notice I have the degrees Celsius there correct because I wrote that. So that's absolute zero. So Lord Kelvin said, let's just take the Celsius scale and make it the same change in temperature per degree, but shift it by this 273.15. So the Kelvin temperature is the Celsius temperature plus 273.15. So absolute zero is minus 273.15 plus 273.15. 0 kelvins, which means that the temperature of freezing water is going to be 273.15 kelvins, and boiling water 373.15 kelvins. So the Kelvin scale is just shifted, and so let's use a different color. Temperature Kelvin is equal to temperature Celsius plus that 273.15. I think it's important that I put it out there. You'll be fine if you just 273.
So we can just do 273.
Yeah. And remember, you'll have these equations. It's not like you need them memorized, but you need to know what the difference is in Celsius, Kelvin, Fahrenheit, be able to work around them. So let's just get some ideas on temperatures. Oh, I want to point out something else. Oh, this doesn't go down cold enough. If you take these equations, you might ask, at what temperature is Celsius and Fahrenheit the same? Well, I can solve that easily enough by taking that top equation in the box and just set temperature Fahrenheit equals temperature Celsius. And so I have, I'll just call it T. T equals 9/5 T plus 32. Move things across, and I would have 4/5 T minus 32. And then you multiply by 5 divided by 4, and you find negative 40. Negative 40 degrees Celsius is the same as negative 40 degrees Fahrenheit. And so physicists with our wry senses of humor like to say, oh man, that was cold, that was minus 40. Is that Celsius or Fahrenheit? And then they laugh and laugh and laugh. Because units are very important to us, but in that case it doesn't matter. And I know, it's silly, that's why I say, tell you this.
I mean, it could be in Kelvins, right?
It could be in kelvins. That makes a difference. So looking at temperatures, some cold temperatures. Absolute zero, 273, minus 273. Notice helium boils here at 4 kelvins. Helium boils at a pretty low temperature. I think it's at 4 kelvins. Oxygen boils, oh man, that's like minus 177 Celsius where oxygen boils. I think that's right. It's in that ballpark. Dry ice is up here around minus 100. Liquid nitrogen is not shown here, but liquid nitrogen is somewhere in this ballpark, about minus 77 Celsius.
So oxygen is boiling right now?
Oxygen is in the gas phase, right? Boiling is going from the liquid phase to the gas phase.
Boiling is when something changes.
So you can freeze oxygen.
Yes, you can make liquid oxygen, but that's really cold. That's right. You would not want to put your hand in liquid oxygen because what would happen?
It would fall off. It would shatter.
It would freeze, and then if you tap it on something, it would shatter. And even if you didn't tap it on something, the cells inside would have burst and they would die. So that would be bad. So we get up here, and we have, water boils at 100 degrees Celsius, 100 degrees Celsius. That's interesting because this arrow points higher than 100 degrees Celsius. Get tin melts, iron melts, a carbon arc lamp. The surface of the sun, 6,000 kelvins. When we get to the high temperatures, we're only going to look in kelvins. We're not going to worry about the Fahrenheit, Celsius anymore. Just talk about kelvins. And when you get to a high temperature, 6,000, sure, 273 does make a difference, but not a big difference. So, surface of the sun, we say about 5,800 Celsius, or, actually 5,800 kelvins. We don't make a big deal out of it. Plasma is what you have inside of a neon light, or what you have inside of these lights here. You have a plasma. A plasma is an ionized gas. And so we have there 20,000. Now the sun is a plasma as well. So this is not all plasmas. It's just an example. The sun has a surface of 6,000. A hot star is almost 10 times hotter than the sun. Most people think the sun is pretty hot because, 6,000 kelvins is hot. But compared to other stars, it's not so hot. The center of the sun, this says 20, more like 15 million kelvins. I should have paid attention to that. That's a big difference, right? Yeah, question?
Would you call like Fahrenheit, Celsius, and Kelvin? Are those like temperature scales? Or?
That's exactly what they are. So the center of the sun is about 15,000 kelvins. This is just rounding off. I think that's why it said 20. And then a hydrogen bomb. Hydrogen bombs are really, really hot. Those are fusion, the same thing that's going on in the sun, just in a different situation. 100 million kelvins. So when we think of hot way down here. But there's things that are a lot hotter. I've already talked about this. Heat. So we've been talking about temperature this whole time. And the word heat has been used, but it's not the thing that I've been focusing on. I've been focusing on temperature. Heat and temperature are important to know the difference. They're not the same thing. Now, it is accurate for me to say, I turned up the heat. And if I turn up the heat, there will eventually be an increase in temperature. But heat is a different thing than temperature. Heat is a transfer of energy. Up to this point, we've talked about energy, and we had work as a transfer of energy. Right? Work was force times distance parallel to that force. Heat is a different kind of energy. But if you put heat into something, you're putting energy in. If you put energy in, what's going to happen to the kinetic energy of the molecules?
You have more energy.
You have more energy, and in temperature, that translates into a higher temperature. So when heat goes into a material, the temperature goes up. So when heat comes into this classroom, the temperature will go up. If heat leaves the classroom, the temperature will go down. So heat is a transfer of energy. And the transfer occurs because you have temperature differences. An important thing is heat naturally flows from higher temperature to lower temperature. So if my body temperature is 98.6 degrees Fahrenheit, and this tabletop is at 70 degrees Fahrenheit, if I put my hand on the table, what direction is heat going to flow? It's going to flow out of my body into the table, which is down. When I said direction, you guys answered correctly. It's not what my brain was thinking when I said direction. So it's going to flow out of my body into the table. I perceive that flow. I can feel the energy is leaving. That cold feeling I have is because of the heat leaving. Whereas if I were to touch this thing when it was still hot, it's not now. But if I was to touch this when it was hot, it's a higher temperature in my body, heat would flow into my body, and I would feel that as well. And if the energy comes in too quickly, my body can't dissipate that energy. The cells themselves get really hot, and that damages the cells, hence burns. So heat, the flow of energy. Temperature, a measurement proportional to the average kinetic energy. They're related, Heat flowing in will increase temperature, and heat flows from hot to cold. I think I have a question here. No, I don't have it here, so I'm going to have it. Let's say I have a big old lake. And this lake has water at 34 degrees Fahrenheit, just a shade above the freezing temperature. And then I put into this lake a little tiny piece of red hot iron. If I add up the energy of the iron compared to the energy of the lake, guys, the thermal energy taking the kinetic energy for each molecule and adding them up, which one has more total energy? It's actually the lake. The iron has more energy per molecule, but the lake has so many more molecules, it's going to have more energy. Now, we don't, notice I said which has more energy. I didn't say which one has more heat, because things don't possess heat. Heat is only a transfer. But the lake has a lot more energy, but the temperature is much higher. The average energy per molecule is much higher in the little piece of red hot iron. So what direction is energy going to flow? From the higher energy per molecule to lower energy per molecule, or from higher energy to lower energy?
It's going to transfer from the higher energy per molecule.
Per molecule. It's going to go from the hotter one to the colder one, not from the higher energy to the lower energy. Hotter is higher energy per molecule.
But it's still higher energy.
The total energy of the water is higher than the total energy of the iron. Because think about it like this. We'll think about it in monetary terms. If we have 300 million Americans that each has a personal net worth of $100, then we have 300 million times 100. That gives us $3 billion. $30 billion worth. And then we have, 500 Americans that have an average net worth of $100 million. And so that's $50 billion. The super wealthy combined here have, I chose bad numbers because the super wealthy have more money. Okay, so let's say it's 50 then. That would be 5 billion versus, what was the other number, 20 billion? 30 billion, okay. So 5 billion in the super wealthy, 30 billion in the rest of the Americans. There's more money for the rest of the Americans, but there's more money per person for the billionaire. And so that's the type of thing we're looking at here. Which direction is money going to flow as far as taxes go? It's going to flow more from the billionaires into the poor because it's the money per person that indicates which way the money can flow. Same thing here, the energy per molecule is what indicates the direction it can flow. Now, this thing called the calorie. We probably all are aware of calories. We count calories when we're feeling lame about ourselves. What is a calorie? Energy. If we look historically, there was a theory of the caloric and the frigidity, that these were fluids that would flow and make things get hotter or colder. But then there was an experiment done that showed that if you do work on something, it gets hotter. It actually started with the observation that in drilling out a cannon, you had to cool it a lot. And the person realized, wait a minute, I'm putting work in, and then I have to cool it, I have to take away heat. And so maybe that work has something to do with heat. And then Joule did an experiment where he actually measured the equivalence between heat and work. And so we now understand that this calorie, the unit of heat that was historically used, is just a unit for energy in heating. And so calorie, one of the weird things in life, this number is rounded off to only 2 decimal places so we don't see it. Different disciplines can't agree on what this number is. I don't understand why. I'm a physicist. To me, that number is 4.186 joules is equal to 1 calorie. But then biologists will say 4.184. And I guess that would make a difference with this rounding, wouldn't it? Question, Hosanna.
So you use 1 calorie with a small c. A big C means 1,000 little
Yes.
c's, right?
That's
So
correct.
When we,
It doesn't say that up there. You're ahead of me.
I took chemistry last semester.
Okay.
Anyways, so when we actually read the calories in our food, it's 1,000 times
Right.
the small calories.
So in your food, if you have a candy bar that's 220 calories, a dietary calorie,
1,000 times bigger than regular.
and dietary calories we write with a capital C, we do as physicists, people who make product labels may not be so careful, is equal to 1,000 calories, which would be 4,186 joules. So when you eat that 220 calorie candy bar, that's 220 times 4,186 joules. That's almost 1,000,000 joules of energy in that candy bar. Now, if you think about it, your weight is, let's say you're a heavy person. Your weight is about 1,000 newtons. 1 candy bar is enough energy to raise you about 1,000 feet, or 1,000 feet, excuse me, 1,000 meters, or a kilometer. That is a lot of energy in that candy bar. Okay. Clarify what you don't understand so I can explain.
What do you mean raisins that many meters?
Well, remember,
Gives you enough energy.
work is equal to change in potential energy. For gravity, that's mg times the change in height. So if your mg was 1,000 newtons, which would mean that you have a mass of roughly 100 kilograms, which, trust me, you all don't. I do. Then you would have that candy bar energy to raise your body a kilometer. It's a whole lot of energy just in that candy bar. And so we're getting lots and lots of energy from what we eat, and then our body's processing and using it. I am out of time. Have a good Monday.